drawing magnetic field lines with the aid of a compass. The magnetic field of a bar magnet can be explored using a compass. If a compass brought near magnetic field, the compass needle will align with the magnetic field lines. The direction of the magnetic field B at any location is defined as the direction that the north pole of a compass needle points to at that location. Magnetic field lines appear to begin at the north pole of a magnet and to end at the south pole of a magnet. However, magnet field lines have no beginning or end. Rather, they always form a closed loop. In a permanent magnet, the field lines actually continue within the magnet itself to form a closed loop, representing the direction of the magnetic field. Usually, to indicate the directions of magnetic field, an arrow is used to show the magnetic field that in the same plane. When the field is directed into the page, a series of cross used to represent the tails of arrows. If the field is directed out of the page, we used a series of dots to represent the tips of arrows. Magnetic flux and its relation to the strength of a magnetic field. A useful way to model magnetic field strength is to define a quantity called magnetic flux, phi. It is defined as the number of field lines that cross a section area at right angles to that area. Magnetic flux equals surface area times magnetic field component to the normal to the plane of surface. Symbols can be used to represent the equation, where the symbol phi represents the amount of magnetic flux. The cross-sectional area is symbolized by the symbol A, while the magnetic field is symbolized by the symbol B. Imagine two circles of the same size that are perpendicular to the axis of the magnet. One circle is located near one pole of the magnet, and the other circle is alongside the magnet. More magnetic field lines cross the circle that is near the pole of the magnet. This greater flux indicates that the magnetic field is strongest at the magnetic's poles. Earth has a magnetic field similar to that of the bar magnet. The north and south poles of a small bar magnet are correctly described as the north-seeking and south-seeking poles. This description means that if a magnet is used as a compass, the north pole of the magnet will seek or point to a location near the geographic north pole of Earth. Because unlike poles attract, we can deduce that the geographic north pole of Earth corresponds to the magnetic south pole to the magnetic field. It is similar as if a bar magnet were buried within the Earth. If a Kappenpost needle is allowed to rotate both perpendicular to and parallel to the surface of Earth, the needle will be exactly parallel with respect to Earth's surface only near the equator. As the compass is moved northward, the needle will rotate so that it points more toward the surface of Earth. Finally, at a point just north of Hudson Bay, in Canada, the north pole of the needle will point perpendicular to Earth's surface. This site is considered to be the location of the magnetic south pole of Earth. It is approximately 1,500 kilometers from Earth's geographic north pole. Similarly, the magnetic north pole of Earth is roughly the same direction from geographic south pole. The difference E between true north, which is defined by the axis of rotation of Earth, and north indicated by a compass, varies from point to point on Earth. This difference is referred to as magnetic declination. An imaginary line running roughly north-south near the center of North America currently has 0 declination. Along this line, a compass will indicate true north. However, in the state of Washington, a compass aligns about 20 east of true north. To further complicate matter, geological evidence indicates that Earth's magnetic field has changed and even reversed through Earth history.